I am Bursa. I am a World Heritage Site from the depths of history. I am a depository of civilizations on the foothills of Mount Uludağ. I am the ancient capital of the Ottoman Empire and its enduring spirit. I am Bursa. I am the prayers and calligraphy of the Ulu Mosque. I am the tiles and ceramics that give the Green Mosque its name. I am the houses of worship in Iznik, once home to Romans, Byzantines, Seljuks, and Ottomans. I am the Muradiya Mosque complex, where life and death, dreams and reality, poignance and joy are contemplated. I am a boundless land of legends, the living cultural heritage of Cumalicuzic, the sun setting on Gölyaza Lake. I am nature's gift to humanity. I am the color green in all its shades. I, a centuries-old sycamore, tones of blue and green, sun and lake, am Bursa. I am the eternal beauty of the Longos forest. I am the rushing waters of the Sai Tabat and Suuchtu Falls. I am a city of flavors, where history meets gastronomy. I am crispy jontic from a wood-fired oven. I am the finest olives and olive oil. I am the birthplace of Bursa kebab. I am köfte with pide and inegern köfte, that is, a paradise of Turkish-style meatballs. I delight palates with sensational flavors, like soft tahini pide and candied chestnuts. I am a land of fresh fruit and nature's bounty. I am paragliding between sky and forest. I am the center for adrenaline and nature sports. I am the timeless shadow puppets, karagas and hajavats. I am handicrafts at Erganda Bridge, a steel knife forged in fire, a smooth silk shawl from Kozahan, a handcrafted Iznik tile. I am the last stop before Europe on the Silk Road, the covered bazaar. I am so much more than a city. I am Bursa.
Hello everyone again. We invite Dr. Rafael CASTRO-LOPEZ from Sevilla University to make his speech. Dr. Rafael CASTRO-LOPEZ has co-authored more than 100 international journals and conferences, and has authored or edited 5 books and book chapters. And also, I personally think the presentation will be very enjoyable. I wish a good presentation for everyone. Now I leave the floor to Chairman of the session, Professor Mustafa Berke Yelten.
All right, hello everyone, and I hope that Eleco has been a good venue for you until this point. And today we will have with us my dear friend and colleague, Dr. Rafael CASTRO-LOPEZ. Although we had some good introduction, I would like to also give some more details about him so that you know him better and his research in more detail. So Dr. Lopez received his PhD degree in microelectronics from the Universidad de Sevilla, Spain in 2005. Since 1998, he has been a researcher with the Instituto de Microelectrónica de Sevilla, currently being a tenured scientist there. He has participated as a researcher in several national and international research and development projects. Moreover, he has co-authored more than 100 international journals and conferences, and has authored or edited 5 books and book chapters. His current research interests include the design and design methodologies of analog, mixed signal, and radio frequency circuits and reliable circuit design. Dr. Castro has served as the general chair and participated in the program committee for several international conferences. He currently serves as an associate editor for the Integration, the VLSI journal at Sevilla, and as an expert collaborator in the ICT area of the State Research Agency of Spain. So I think that this talk will be very much of interest to you, especially if you're interested in microelectronics domain. So with all that, I'll leave the floor to my dear friend, Rafael. Rafael, the floor is yours.
Hi there. Hi, everyone. Thank you very much for the introduction, for this kind introduction. And I would like first to begin by thanking all of you, thanking the organizers of the conference for this invitation. It's a really an honor to be here among such other important speakers in this renowned conference. So let me share my screen. Okay. Can you see the slide? Yeah.
Yes, we see it.
Okay. So the title is Two-Phase Variability Challenge in Nanoelectronics, and Mitigation and Exploitation being these two phases, and what is the road to get there. So my research has led me from layout automation to systematic design methodologies of web design, and lately into the world of security and reliability. But today's talk deals with variability in the world of semiconductors and integrated circuits, a challenge that we all know needs to be dealt with. Surprisingly has can have huge benefits for certain important and critical applications. And as you already know, there are many different ways to understand variability. It changes from what was intended. In the world of semiconductors and integrated circuits, this would be a simple but effective way to organize all those variations, the one you see here in the slide. And at the end of the day, we are interested in performances and changes from that intended performances, and eventually leading to concepts like reliability, yield, lifetime, degradation, and so on. And here you can see a fairly complex taxonomy of variability in the world of semiconductors, where main classification is done according to the damage that is done, either as a degradation or as a variation from the performance. Don't mind the bunch of acronyms here, although you are probably already familiar with many of them. They will be clear during this talk. This particular taxonomy also attends to the scope of the variability, from wafer to circuit to the type of gate. But for me, this is a simpler way to understand these variations, where time here is the differentiating factor. Either they appear at the beginning of the life of the integrated circuit or during its lifetime in many different shapes and forms. Variability appears at the point of manufactures of the integrated circuit in what is known as time zero variability, which can be either random or systematic, and which are pretty well known in the industry, and they are a familiar face for every designer. On the other hand, we have variation that rise with time, like RTN or SEU, or transient effects like aging, with phenomena such VTI, hot carriers, TTDB, or electromigration. In this talk and the interest of time, I will only cover the ones highlighted here, RTN, VTI, and hot carriers. One important takeaway here is that stochasticity is key in modern nodes, modern integration nodes, which means, for instance, that two equally designed transistors will not age equally. And at the end of the day, what compromises reliability of the integrated circuit. But what's reliability in this context? Well, at the top of the slide, you can see the typical failure rate over time bathtub diagram with different stages of infant mortality, useful life, and wear out. While reliability here at the bottom typically shows a decay with time up to the circuit end of lifetime. Reliability is actually a measure of yield, with yield being the ratio of, let's say, working circuits to the total fabricated samples as it evolves over time. The lifetime is dictated by the moment when the reliability goes below one predefined critical threshold. So To maintain the effective performance scaling, the outside electric fields and current densities have been increased over time, and the reduction of lateral transistor dimensions or the introduction of new gates materials are all reducing the circuit reliability, turning this into a critical problem as technology continues to scale, as shown here. With the scaling also, the bathtub diagram gets way worse, and reliability is dramatically impacted with scaling as well. And the worst consequence here is that the lifetime of the circuit gets critically shortened. And why is this important? Why this is critical? And why dealing with variability is important? For one thing, think of the present shortage of integrated circuits, for whatever the reasons there may be. Perhaps it's now more important than ever to extend the lifetime of the circuits. And to do this, we need to fight against any possible source of degradation. Also, the International Roadmap for Devices and Systems has claimed in the latest report that reliability is a critical concern, with recommendations like optimal reliability evaluation methodologies are needed. It's also needed to decrease the process margin and increase variability, which drives to develop an in-depth understanding of the physics and efficient reliability engineering tools. Also, the Electronic Component System for European Leadership latest research agenda puts reliability together with security here as essential capability that impact each and every one of the key application areas here, like health or transportation. In this regard, it is very interesting to note that security and reliability are grouped here together. Perhaps this is a hint that variability impacting closely reliability is also a factor to account for insecurity, as we will see later. Eventually, there is an opportunity in every crisis, right? Maybe something good can be obtained here from the variability. So variability, as traditionally considered, is clearly a foe, right? A foe that comes in two shapes: time zero, time-dependent variability. A foe that needs to be mitigated. And this is the first phase of variability and one of the main sections of the talk. But variability can also be exploited for one of the essential capabilities that is critical to many key applications. And this is security, or more specifically, hardware security, a discipline originated from cryptographic engineering, which consists in providing vulnerability protection coming in the form of a physical device rather than software. This is the other phase of variability, the opportunity from the crisis of variation and degradation. But in any case, either to mitigate or to exploit, one thing is clear: the sources of variability must be fully understood, modeled, and incorporated into the tools that we use to design our circuits on a daily basis. These three components, characterization, modeling, and reliability-aware simulation, are the common ground of the presentation that will enable both mitigation and exploitation. So let's start with characterization, the understanding of the sources of variability. Not much to say here about TCV, as this is a very well-known phenomena. Models are readily available, and the simulation tools already know how to incorporate this into our design flows. Now for TDV, I will consider three main effects: random telegraph noise, bias temperature instabilities, and hot carriers. Okay, so all these three stem from the presence of defects or interface traps that appear during fabrication or possibly are generated in the transistors. Think of them like irregularities from the in principle ideal crystalline structure of the semiconductor. Random telegraph noise is a probabilistic capture or emission of charge carriers from these effects. And these captures and emissions are spontaneous and intrinsically random in nature. This is RTM. As for VTI, which includes a negative and positive, this is a major cause of threshold voltage variation increase actually in the transistor during the lifetime. This effect occurs in a transistor when a high voltage is applied to the gate. Then positive interface traps are generated at the silicon or silicon dioxide interface, and as a result, the threshold voltage increases and the MOS transistor becomes slower and even fails to meet timing constraints. It is worth noting here that this effect is also partially recoverable. That is, if the biasing stops, the degradation recovers. Hot carriers occur when carriers are injected into the gate dielectric during transistor switching and when a high VDS, a drain voltage, is applied. This effect is a function, a very important function of switching activity, and degrades the circuit by shifting the threshold voltage as well. How important is TCV and TDV, and more in particular the TDV, the time-dependent variability in all designs? This example illustrates this importance. This is for CMOS ramps, and show how thin gets the design margin when considering all these sources of variability. If not dealt with, or minimized or mitigated in some way, things are getting really complicated. Technology scales down. So how do we characterize all these effects? For TCV, the procedures are very well known by the industry. But for aging, degradation, characterization is done with what is known as accelerated aging. That's pretty much what happens with us, with human beings, because the stress accelerates our process of aging, right? For integrated circuits, we use the same concept, like mapping 10 years of performance into 2 minutes in the lab using stress. And what we use here are elevated voltages and elevated temperature and time. Accelerated aging helps here, and what it does, in a nutshell, is to exacerbate the physical mechanism behind aging, so that the key parameters can be extracted and then fed into a proper model. This will be clear later. So accelerating aging is rising bias and temperature during a certain period of time. During the stress phase, for VTI, for example, the gate voltage is elevated. And for a hot carrier test, both the drain and the gate voltage are elevated. Then we switch these stresses off to monitor the recovery of the threshold voltage. These should be done on thousands of transistors, so we can have a better statistical account, and with different stress and recovery times. So we have different experimental windows, and we can have different snapshots of capture and emission of charges with the defects, like seeing into the future. The typical test is like the one shown here, composed of several stress and recovery or measurement phases, with the same duration for each recovery phase and increasing duration of stress phases. This is an example of what happens in the transistor. During the stress phase, the threshold voltage increases, and when this is for different geometries, and when the stress stops, the threshold voltage start recovering. In some manners, and never recovers actually towards the fresh value of the transistor voltage. So one common approach to implement accelerated aging is with probe stations, where only one device, one transistor at a time, is characterized. The problem with this solution is characterization time, especially if you want to test thousands of transistors. For instance, a simple 5-cycle BTI test of 100 devices with the stress and recovery times in this table will take 14 days. Take, for example, 5 different bias values of BTI, 5 for hot carriers, and only 2 temperature values will take us 3/4 of a year. That's why we resorted to arrays-based ICs, with which it's possible to parallelize the characterizations of hundreds of devices, thus reducing considerably the characterization time. And here's a photo of Endurance, one of the chips that we designed to characterize TDB. This was published in the IEEE Journal of Solid-State Circuits in 2018. And this chip is one of a kind, because it covers many different variations, different effects, different mechanisms, has more than 3,000 transistors per chip with eight geometry variants, and more importantly, it uses the parallelization scheme that we reported, with which we can reduce the 14 days to only 14 hours. So this is essential for characterizing these phenomena, which we know in the modern integration nodes are going to be stochastic, and we need a lot of characterization here. This chip deserved the attention of no other than Intel, which naming one of the most important achievements of 2020 as far as reliability characterization was concerned. Of course, there are other very remarkable efforts in this area, like the setup by Jaffa et al. In 2021, aiding, among other interesting features, the capability of analyzing the role of body bias in time-dependent variability. This is indeed a hot topic with, as you can see here, remarkable achievements. So let's move to modeling and simulation. There are many options for modeling. One of the first was the reaction diffusion model, which explained TdV as the breaking and rebonding of hydrogen silicon bonds. This is a simple compound model, but it's deterministic, and above all, it failed to fully describe BTA recovery, the recovery effect when stress stops. Other options are empirical solutions that fit experimental data. These are common practice in the industry, but not very accurate because stochasticity is lost. And finally, the more trustworthy of the models are the trapping ones, which consider a number of defect states with different energy level, encounter and emission times, which leads to different increases in the threshold voltage when a trap captures a charge carrier. And this model is way better for stochastic modeling. How does this model work? Essentially, it considers the presence of defects in the gate, as I mentioned before, and each defect can be either occupied or empty, occupied by a charge carrier or empty. The defects are characterized by 3 parameters: the capture time, the emission time, and the impact on the transistor threshold voltage of each defect. When the defect is occupied, the threshold voltage increases and the current decreases. When it is empty, the threshold voltage decreases and the current increases correspondingly. With this view, one model that is very complete and accurate is the probabilistic defect occupancy or PDO model. This model, the PDO model, needs several things in order to be used in simulation. First, the distribution of defects in the biplane emission capture time. That is, which emission and capture times are most probable. This defect, the defect, which we call here the defect, looks like an ellipse in this plane viewed from above. Actually, it's 3D dimensional. Here in this axis, the defect density. This ellipse depends on the biasing of the transistors, and it's something that you need to characterize. Second, it needs the number of defects, or rather the density of defects in the technology, and the impact of the defect in the, for example, threshold voltage. These 3 elements, the density, the number of defects, and the contribution, are the ones that you need to characterize, and that's why you need a characterization framework capable of doing that for many devices. Then the PDO model also uses something that is called the probability of occupation. Essentially, it's how probably that a defect is occupied depending on the biases, on the bias of the transistor and the time that it's been under that bias. Okay, that is the model. But to better understand it, I think it can be useful to see how it is used in a simulation of aging. We have the fresh circuit, for instance, this very simple diode connected PMOS with a current source. And then a simulation is carried out to find out the voltages in the transistor terminals. These give us the density of defects and the probability of the occupation and time 0. To calculate the degradation in the threshold voltage at a final time, we assume that the biasing stays the same during that time, and we obtain the probability of occupation that final time. Then we generate a sample of the number of defects, resulting in these white dots you can see here, with the size of each dot. Also, a sample of the impact on the threshold voltage. And this is done according to the density of defects. Then, using the probability of occupation that we have calculated at that final time that we want to estimate the degradation for, these are the only defects that remain occupied according to the bias for the whole time from time 0 to t final. These give us the total degradation. Those remaining defects give us the total degradation. And if we somehow Monte Carlo this, we will have a distribution for the delta of the threshold voltage and overall a stochastic image of the degradation. In this way, we can have the H circuit at this final time by, for instance, adding a voltage source at the gate, mimicking this delta of threshold voltage. In fact, there are many approaches to realize this H circuit. So the description that I just gave is a simplified version of what really should matter, especially for analog circuits. Why? Mainly because of two reasons. First, because there is a bidirectional link between biasing and aging. Second, because we have to take into account simultaneously time-zero variability and time-dependent variability, as well as their correlation. This has a huge impact on simulation runtime, and is therefore mandatory to handle this CPU time versus accuracy trade-off very, very carefully. Let me explain this a bit more. Even if the stimuli are constant, biasing cannot be considered constant because of this feedback. Okay, so a direct extrapolation will commit a certain mistake because we have assumed that the stress is constant and eventually it is not. So the solution is to include intermediate steps to update those stress conditions. And commercial tools already include this as an option, either as a linear or logarithmic distribution of steps. But this linear or logarithmic commits many mistakes. So recent solutions go for an adaptive algorithm that updates this stress condition when necessary. And these are two approaches here. One, to define how accurate do I want to calculate my degradation, which minimizes the CPU load, or to define the number of steps, depending if I have certain CPU budget or certain simulation time that I cannot go over. And you can see here the comparison. If we take 1,000 steps as the golden reference, you can see here that an adaptive scheme in red attains less error when compared to the golden reference. It attains the very, very small error way earlier than the other two linear or logarithmic schemes. The other concern was how to handle both TCP and TDP. The distributions time zero evolves with aging, with the degradation, and you have to track the degradation of each sample. And this is computationally very expensive. Essentially here, the more CPU, the better accuracy, but the lower the simulation time. And the less accurate we can afford to be, the faster we will be, the simulation time. And let me put a clear example of how critical is this. We have a stochastic distribution for time zero and time-dependent variability. It's like estimating how each time zero sample will age stochastically. So just to show you how bad the situation is, if we need, for example, 1 second for each transient, we only take 30 samples, Monte Carlo samples for both the distribution, time zero and time-dependent, and take 30 steps to implement, the updating of the stress condition. The total time required for this simulation will turn to be 2 with 30 zeros, which, if I'm not wrong, is a bit unaffordable. So really great accuracy here, but really impossible on CPU times. So it is necessary to come up with alternatives. For instance, at the top, not doing Monte Carlo for all the time-dependent variability, just computing the degradation of the mean. Or here, a button only computing the aging of the mean of time zero and aging only the mean of both distributions. Which option is the best? Well, both or none, depending, for instance, on how strong is the correlation between the variation or time zero and the degradation by aging. If this correlation is strong, that is, the aging depends on the particular time zero value of the threshold voltage, then option 2 really loses this information. So it depends. There are simulations out there. There are very remarkable academic options like the one from Marikawa or Rafael, and other commercial solutions like BERT from 25 years ago, or Mosran from Synopsys on RealExpert, and Legato from Cadence. The majority of these tools uses deterministic models, except, I believe, for Legato. But things are evolving in this department, and for instance, Cadence has also a very interesting option that I believe is the way to go, the Unified Reliability Interface, which is a way to wrap up any custom model, deterministic or stochastic, to be used together with more mainstream simulators like Spectra. We have also developed an stochastic simulator, which is called CASE, which uses the PDO model that I explained before. The adaptive time step algorithm includes TDB and TDB with many options, and includes as an option as well the lifetime estimation of the analog circuit. So this wrap-ups characterization modeling and simulator. These are the pillars, the basis, the common ground that you have to take into account to mitigate or to exploit the variability. And now let's go for mitigation. Mitigation is just taking these time-dependent yields that we saw before, defining the lifetime of the circuit, and pushing it so that the lifetime is extended. And there are two flavors here for reliability aware design for these mitigation techniques. Prevented, that is, during the design time of the circuit, implement certain rules, certain guard bands, such as the circuit is robust. Or reactive, the solutions will try to instill some capabilities in the circuit to react and act to its own aging or to external varying conditions. There are many works here. The research is wide, and the taxonomy is huge. And this is just an illustration of a handful of mitigation techniques. I wanted to show you the to convey the idea of how hot this topic is. Recently, machine learning has entered the picture, as in many other fields, and this has really promising consequences. One of the most common practice of proactive techniques is the worst-case design, where the designer tries to anticipate the degradation, for which having accurate models and efficient reliability simulation is very important. And one simple technique will be to add guard bands during design. Let's say, add enough room to still fulfilling the specification when aging is present. However, this many times leads to over-design, even when having accurate models and simulators, since the designer needs to handle many specifications at the same time, many balls in the air, and it's not easy dealing with that many trade-offs. So that's why adding smart guard bands is way better. And I mean designing the circuit with certain guard bands, but not at the expense of wasting, for example, too much power or too much area, or both. One approach to a smart guard banding uses a simpler kind of artificial intelligence, as the one shown here, where the link between the simulator and the optimizer is established, and the optimizer is perfectly one that is evolutionary, can handle many goals. So in designing our circuit, we're interested in is it has many performance to optimize, while also including things like maximizing the lifetime or improving the yield over time. There are two types of optimization-based reliability aware design. The first one is, as I mentioned, maximizing the lifetime to extend the life. And the other is to optimize the performance while optimizing at the same time the yield, the reliability over time. It's like, in this case, in this latter case, like pushing this distribution of this circuit in the speed gain plane, and at the same time minimizing the portion of breakpoints so yield is maximized. And this is a picture that I think conveys very well both types of optimization. This is a lifetime maximization. It's like extending your life way beyond the usual, while your yield and performance optimization is like being at the best shapes of your life, even at a certain age. Even though Mick Jagger, I believe, has a way better shape than many people of his age. One important thing here is that, as you probably suspect, simulating aging with a great deal of accuracy is not cheap at all. And mitigating through simulation optimization will be even worse, even because thousands of simulations are typically involved. So it's crucial to have smart optimization algorithms, like the one here, where the individual or the candidate solution goes through many phases, each phase more complex in computation. And the idea here is that we do not waste CPU time, simulation time to calculate, for example, lifetime on bad candidates that we know, for example, that does not fulfill specification of time zero. With these smart techniques, optimization is accelerated and exploration of the time space is improved as well. One example for this amplifier of lifetime maximization, where we have the optimization achieves a lifetime of 30 years approximately, which individuals with high dizzy gain has lower lifetime. This same optimization problem was carried out without using that smart CPU allocation technique and did not obtain any solution at all. This is an example of optimization with yield and performance as well. And as you can see, there are many options to go with for mitigation, and the research field is hot right now, and machine learning has entered the picture, so many promising consequences here. Now, we have seen mitigation, and let's see exploitation. We can see that we have seen that TZV, time zero, time-dependent variability can be mitigated. Both approaches, proactive or reactive techniques, has pros and cons, obviously. This exploitation is like a side benefit, a surprising side benefit. And one major field where variability is not a foe but a friend is hardware security, and in particular when secure authentication or identification is needed. Consider, for instance, an IoT device that needs to be authenticated outside a trusted location here. If this IoT will have sort of a fingerprint, an ID, this will be used to compare with the database to know if the device is authentic or not. Traditionally, this has been done with non-volatile memories, but these are prone to malicious attacks and extraction. A solution will be the physically unclonable function, which are harder to imitate or predict by a malicious attacker. How is this so? Well, in essence, a physically unclonable function, a POF, is a device that exploits inner randomness introduced during manufacturing to give a physical entity a unique fingerprint. In other words, we can use time zero variability, for example, to obtain an identification with this physically unclonable function. There are many POFs out there, and this example right here uses the SRAM cell, which is one of the most common ones. This is formed by two cross-coupled inverters, which has an store value, can be written or read with these bit lines by enabling these access transistors. It's very typical SRAM cell. How is a POF implemented with an SRAM? Well, ideally, these two inverters are symmetrical, and when we power up the cell, ideally the cell reaches a metastable state. However, due to some noise in the circuit, it either goes to 1 or 0. I mean, this node Q, for example, goes to high voltage or low voltage. And this is caused by the asymmetries in the inverters that are caused by time zero variability. So when I power up the cell, it will either go to 0 or to 1. And if we have an array of SRAM cells and power them up, we can attain a collection of ones and zeros, which is a response from the proof, and that can be used in security protocols to provide identification of the device. Here, blacks, for example, are ones and whites are zeros. However, TDP comes here in the picture, and factors such as temperature and supply voltage variation or circuit aging may threaten this reliability of SRAM-based paths. And what do I mean by reliability? Reliability here means that from time to time, when I use the path to get a response, to get this bit string, sometimes due to aging, the bit string will not be the same. So it's like the fingerprint will not be the same from time to time. So aging threatens the reliability of POFs used for security. As you might be thinking, we have the case here where we are exploiting TCP for security, while the TCP is acting as a degradation that should be as well mitigated. For example, there are many methods. One of them is called dark bit masking methods, which essentially discard these unreliable bits from time to time. This bit, for example, changes from 1 to 0. And these dark bit masking methods try to find out which are those unreliable bits. And we have integrated the circuit to investigate this issue and to come up with dark bit masking methods. And this is an integrated circuit with 832 SRAM cells with the same philosophy as the Endurance chip that I shown before. And these chips allows the analysis of the path of the SRAM path under varying conditions like aging, temperature, and supply. And the method that we have come up with is based on the data retention voltage, which is the voltage that the minimum voltage for which the SRAM cell retains the value stored in the nodes. And this method is very simple. We just write the non-preferred value on the cell, we lower the VDD, and we determine the data retention voltage, the value of the voltage, the VDD voltage, which the non-preferred value that we have written is lost. And with this method, we can identify those cells that are more reliable from those that are weaker. And this method is even able to identify those cells that will be more reliable even in the face of aging and temperature. So far I have shown you a way to exploit variability for security, and we exploited in the SRAMs the time zero variability, but there are other ways to exploit not only time zero, but time dependent variability. For example, this paper here, this is a very recent topic. I mean, it's very, very new, but this work here shows how to use random telegraph noise, which is a transient effect, a time-dependent variability effect, to use random telegraph noise together with ring oscillators to create a path, to generate a secure identification. And essentially what it does, it counts how many transitions from the ideal frequency of oscillation of the ring oscillator there are, and compares that number of changes, with other oscillator. And this allows us to extract a bit string as well. So not only you can exploit time zero variability, you can exploit as well time dependent variability. And as you can suspect right now, these time zero time dependent variability is very, very interlinked to each other. When I create a path using time zero variability, I have to take into account that time dependent variability or aging can impact the performance, and come up with methods to compensate, to mitigate while exploiting. So it's not separate phases of variability, they are very much related to each other. Another interesting application of variability, something that we can exploit in the field of counterfeiting. Counterfeiting of electronics is a long-standing but evolving threat, and it is reported that there is one counterfeit part reported every 15 seconds, and that $169 billion is the risk per year for the global supply chain that counterfeit brings. Counterfeits are expensive and time-consuming to detect and replace, actually. So what is a counterfeit? It can be many things. It can be an authorized copy of the chip that may not conform to the original chip manufacturers, or a defective chip, or one that is sold as new or working, a reused chip, etc., etc. The impacts of counterfeiting are many, from public safety to national security to criminal financing, or any other types shown in this slide. Fortunately, there are many detection approaches to counterfeiting, and one of them, pretty curiously, is aging, with methods like sensors to detect the real age of the circuit that is sold as new, including machine learning techniques, or tampering protocols that allows us to know if the circuit has been tampered with. This is an illustrative example of how aging helps. By fingerprinting the delay in a digital path, it is possible to know if an integrated circuit has just been reused just by looking at the delay and comparing this delay with the one that should be if the circuit was sold as new. Within a statistical margin, it is possible to detect this delay degradation caused by aging and know if the chip is new or sold as new, but really was reused. So, to conclude, I hope I have piqued your interest with this two-phased view of variability in the modern semiconductor industry. But whatever solution, either way, to exploit and mitigate, to create more robust integrated circuits, more long-lived ones, or better security primitives, the chain characterization, modeling, and simulation is a fundamental pillar. And I also hope that get you to know a bit more about all the interesting challenge that every piece in this puzzle brings in the field of semiconductor reliability. I think that's all. Thank you very much for your attention.
Okay, I think, Rafael, this was a wonderful talk. I really enjoyed it from the beginning to the end, and it was very informative and actually covered a big scope. If I take a look at it, it's just started from the very physical basics, but now we went into applications in the cybersecurity. I mean, in general, the security aspect of the circuit. So I have a few questions actually here myself. So one of the questions that I would like to ask you is actually, how will this go on with the newer technologies as we are descending into now sub 10 nanometer? Are these challenges going to be more exponentially increasing, or do we face a challenge of linear scale? What do you think? What's your take on that issue? Because this is a very burning issue as we are now opting towards, the 3 nanometer, 2 nanometer, 1 nanometer. How will this play out? What's your perspective on that?
Yeah, I believe this problem gets way worse, maybe exponentially even. And with scaling also appears new structures like FinFETs, for example, all the materials, although will have to be investigated as well in depth. But I believe, all in all, this will get worse until we come up with solution for specific structures or devices. But so far we have in our laboratories we have used from the 65 nanometers technology down to 14 nanometers and 28 for FinFETs, and the variability is there. In one way or another, the variability is there. And if we are talking about, for example, RTN or BTI, it gets worse. Definitely gets worse. I don't know how, if it will get exponentially worse or linearly worse, but it will get worse for sure.
Okay. We have also one question from the audience that should be also asked to you, I guess, Rafa. Can you explain a little bit more detail exploiting the counterfeiting detection techniques in general? That's what it's trying to ask. So what can you say about, in a little bit more detailed, exploiting counterfeiting detection techniques? Sorry for that.
Mm-hmm.
What do you think?
You can see the screen right now? Yeah,
I can.
Yeah. Actually, the thing here with counterfeiting is that it is an expanding field today. And what I can say here is that the sensors based on aging are one of the main research lines, but there are also other, like shown here, which uses the security primitives that I explained before. So you can exploit time-dependent variability or time-zero variability for security, but also these primitives can be used as well for detection.
That's a big point. Yes.
Yeah, it's a very interesting topic, and the thing here with counterfeiting, the main issue here is that the basis is, okay, so I have a circuit that I don't know if it's reused or not, and I have to compare something within this circuit. And most of these techniques, essentially what it does is to compare the age of the circuit.
Mm-hmm.
But to compare the age of the circuit, you have to build something within the circuit that is constantly working, no matter what, that is probably transparent to the main function of the circuit, that is added to that circuit, and it's constantly working. And the thing here, the difficult thing here is that you have, on many of these approaches, you need a reference.
That's right.
Either at the final manufacturer, you generate a reference, and there that reference you're used to compare with the actual age. And other approaches, I believe, more efficient approach from my point of view, are those approaches that do not need a reference. I mean, do not need something to be analyzed at the point of manufacture after fabrications and stored probably in a non-volatile memory to compare with. Those are the most interesting one. And many of the POFs applications are based on that idea. The idea that I don't have to know something beforehand to compare with. Those other ideas are based on the fact that you get a behavior and you know that behavior, and every time what you measure separates from that behavior, you know, or you can know how or the age of the circuit as well. So here with the counterfeiting techniques, you have two mainstream approaches: one that uses a reference and one that does not use the reference.
A side question to that problem that actually pops up in my mind is actually what is going to be the cost of these counterfeiting techniques to my circuit in terms of the power, in terms of the area. Would it account to some big chunk, or should I not be worried about it at all? Or what can you say about that one? The hardware cost.
Yeah. Hardware cost. The solutions can be pretty simple as well. You can use like one oscillator or even two transistors, just two transistors. So you have a reference of the behavior in terms of RTN or BTI of these two transistors, and then when you get the chip, you want to know if these chips have been reused or not. You see those two transistors and compare the age of these two transistors. So maybe just two transistors. Actually, most of the paths, most of the physical and chemical functions in hardware are very simple. They're just a collection of transistors or a collection of ring oscillators, or a collection, or even they will use something that is already in the chip, like the SRAM cells. Mm-hmm. The SRAM cells that you can use, you can also use those SRAM cells to implement the security or the counterfeiting techniques.
And the
So I
best
would
part of
say,
it will be basically that even if this is repeated by some other people, it's not going to be the same because the variations are random. So you cannot really copy it over, even though you have the similar structure.
that's
By
right.
somehow you can't really have the exact same thing. So therefore,
That's right.
it's not
That's
going
why
to be
it is called physically unclonable, because it
exactly.
is impossible to copy that, because it's a physical manifestation of the randomness of the entropy in
That's right.
this entity, in this chip.
One last question I have, because we have a little bit more time, and I haven't seen any other questions popping up since we are having this conversation. Maybe it's also going to be useful for the audience to listen to. Would be the calibration techniques. I mean, the calibration techniques for mitigating the reliability. That is something that might also be regarded in my view, especially now. Of course, we know that digital calibration circuits are also somehow aging, but maybe you somehow keep them intact for the operation. What do you think about that? Would it be kind of too much of a hardware-oriented solution, which needs a lot of area, or do you think that's also possible solution like the digital assisted circuits that are now so popular? What is your take on
Do you
that?
mean in the mitigation field?
So, for example, your circuit has aged and
Mhm.
you are recalibrating your circuit from time to time so that
Yeah.
it is still working. And you don't need to worry about it at all in the design time because you always keep in mind that, okay, I have my calibration circuits. Even if my circuit just ages, I can recalibrate it and I don't need to worry about it at all. The molding or whatever optimization, I don't need to worry about it. What would it be somehow a solution, or would it have its own flaws in itself? What do you think?
Yeah, that's a solution too. I mean, you can use the recalibration approach to mitigate the variation of the variation in the circuit, but you have to take into account that those circuits that you are using to calibrate also age.
That's right.
You have to be designing them very carefully, perhaps with a different type of transistors. For example, in the chip that we use to characterize aging, we use some part of the chip, as you probably know, that
Yep.
are more robust to the aging,
Right.
because there are other types of transistors.
Yeah.
And if you do calibration, you have to take into account the variations and the degradation of these circuits as well. So that may be one solution. Yeah, there are many options here, and it depends, I believe, on the application as well,
That's
or
right.
the application field. But for instance, many sectors use redundancy. They just
That's
put
right too. Yep.
different circuits.
There you
So
go.
one fails, then I get the other.
That's right.
You cannot use that for example, for space applications, because every kilogram that you put up in the space costs you like €1,000,000. So you have to be very careful there, and you have to take on account when you go to space for other degradation sources and so on. But
Exactly.
that's why I mentioned.
The
Yeah.
triple modular redundancy that's there. I mean, the TMR is actually very popular, and that's actually also how you can resolve some of the issues, like especially the ones that you are meeting in space, like single events, etc. That's going to be really a problem, and that's not easy to solve with the known techniques that we are already using. So the only way, as you have put it out, would be just repeating the circuit and have it 2 or 3 on your. I'm actually have it 3. If there is going to be a majority voting, like if just one fails, two still are working. That's the. And maybe before we just hang up, one more thing is that you mentioned a couple times the machine learning. So the machine learning is now becoming really popular. Again, it's similar to my first question. What's your take on that? How will machine learning be playing out in the next decade for this particular area of electronics? I mean, for aging and variability mitigation. What do you think that machine learning, would that be a big task, big chunk, or what do you think?
I don't really know here. I don't know if again is a buzzword, is a hype with machine learning or artificial intelligence, because many years ago we used to talk of artificial intelligence, then somehow disappeared, and now it's rising again.
Exactly.
So I don't know. I don't really know. I wouldn't dare to forecast something in this field, but evidently we have now deep learning. We have more computation power, more efficient simulation techniques in this sense. And I believe it depends on the application. For analog, it will be still harder because analog is always hard in terms of automation or systematization and so on. But for many other applications, like I mentioned, like counterfeiting or security, they're already there. I believe they will be success in this field.
One more thing maybe about machine learning is that, as you have mentioned, is that its capability as fitting, especially with deep neural networks, that capability will significantly grow and has significantly grown. So even if we have a more challenging task in, let's say sub 10 nanometers reliability, maybe in terms of modeling, maybe machine learning will come to rescue and will help us with that, and maybe it'll guide us in the next new technology. So as you have shown in your wonderful presentation, people have stumbled in problems, but the problems have been resolved with innovative techniques, with new perspectives. Especially the one perspective that you have presented was really useful, showing that TZV can be a solution by itself to a burning question. So time will show us how the new techniques will be guiding us in new problem solutions. But it was a wonderful time with you here, and we are very grateful to have you as one of our invited speakers. I hope the audience has also benefited and liked this great presentation. Well, thank you very much for being here with us, and I hope you also like this presentation and this event.
Welcome. Thank you very much.
All right, this will conclude our session for today, and I hope that you also enjoyed the presentation. I wish you a great evening here in Istanbul. Bye-bye for now.
Bye-bye.
We would like to thank Dr. Rafael CASTRO-LOPEZ for this valuable presentation and descriptive answers, and also thank Professor Yelten for chairing the session. Dear participants and guests, I hope the second day of ELECO 2021 program went well for all of you. Our conference is over for today. We are going to continue with the Zoom sessions tomorrow morning, and we'll start at 10:30 a.m. Also, in tomorrow, we have one distinguished invited speaker. Now we are ending our live broadcast for today. Hope to see you in tomorrow's live broadcast. Have a healthy and nice day.